Okay, today we're going to talk about similar triangles. Something you did in geometry, we need to bring it back here as we study trigonometry. And our objective today is to find missing sides of similar triangles. So let's first talk about what the word similar means. Similar, they are the same shape, different size. Okay, a model car or ship, model ship. Okay. Same shape, different size. In triangles, if we have two triangles that are similar, these are the same shape, different size. Okay. These are corresponding angles. These two angles correspond to each other. They're in the same place in the triangle. Corresponding angles are congruent. They're the same. If one is 20, the other is 20. Corresponding sides are proportional. And that just means that if this side is half as big as this side, then this side is half as big as this side. They're proportional. Okay? So we might have something like this. Triangle ABC is similar to triangle DEF. And we might have the triangles look like this. Okay? And then, again, same shape, different size. So here's triangle ABC and DEF. And if this is 2 and this is 5, if this is 1, we can figure out how big that side is by setting up a proportion. And there's two ways to set up the proportion, and I'll show you both of them. We can say, okay, 2 is to 5. This side here to this side equals 1. We go back to the triangle we started with, 1 over x. And then we can use our trick we learned before that we multiply 1 times 5, the two numbers that are diagonal, and we divide by the number diagonal from the variable. So we would divide by 2, and that would give us 2.5. So x, this side, would be 2.5, which makes sense. Okay, this is 2.5. 2 times 2.5 is 5. 1 times 2.5 is 2.5. Now, some of you won't set up the proportion that way. You may set it up this way. You may use both the sides in this triangle first. So you would have 2 over 1 equals, and then go back and start with this one. You started with here, so start with this one, 5 over x. Now those two proportions are the same, and you'll get the same answer either way. The way you can tell that they're the same is look at the diagonals. I got 2 and x on this diagonal. I still have 2 and x on that diagonal. Here I have 5 and 1. Here I still have 5 and 1, they just switch positions. As long as the diagonals remain the same, the order doesn't matter. As long as both these numbers are still on the same diagonal, those proportions are the same. And if we use our trick of multiply the two numbers across and divide by the one diagonal from the variable, x equals 1 times 5 divided by 2, which is exactly what we had before. Okay? Now, this actually is a very useful idea, and if we have a tree that we want to measure the height of, we're not going to get out a measuring tape to measure the height of the tree. That would be very, very difficult. However, if we have the tree has a shadow, and we see the sun's rays coming down like this to the end of the shadow there, so it looks like this. This is the sun's rays. Okay. And we have over here a yardstick, which we know how tall the yardstick is. A yardstick is 3 feet tall. So the yardstick also has the sun's rays coming through it. And we can measure the shadow of both the yardstick and the shadow of the tree. Now if the shadow of the yardstick is 3.5 feet, and the shadow of the tree we measure to be 23 feet, we have enough information to do what's called indirect measurement. We're going to determine a measurement without actually measuring what we want. We're not going to measure the height of the tree. We're going to use other measurements to get the height of the tree. We'll call it h, the height of the tree. And again, these are similar triangles. So now we can set up a proportion. Well, I want to find side h over, and I'm going to go to this one, 3, equals, and then we go back to this triangle, 23 over 3.5. Right? So we follow our rule again. H equals, we multiply the numbers that are diagonal, so 3 times 23, and divide by the one diagonal from the variable, that should be the 3.5, and that turns out to be 19.714 feet. Okay? We can tell that that is a reasonable answer. And it's a reasonable answer because if we look, the shadow of the yardstick is 3.5 feet. It's a little bit longer than the yardstick is itself. So if the shadow of the yardstick is longer than the yardstick, then we expect the shadow of the tree to be longer than the tree itself. And sure enough, it is. The shadow of the tree is 23 feet, and the tree is actually 19.71 feet tall. Okay.